All right, so in this chapter, we're going to be taking a look specifically at the electron as the main subatomic particle, and we're going to see how it influences some of the characteristics of atoms, and then we're going to see sort of a global look at how it influences some of the trends on the periodic table. So there are a couple of things that we need to make sure that we know of or remind ourselves as we get into this chapter. We're going to be doing a couple of calculations that involve a little bit of algebra, and we're going to recall and remind ourselves of some of the relationships we learned back in the earlier chapters, specifically working with numbers and then also using scientific notation in addition to using those metric prefixes we learned back in chapter 2. All right, so we're going to incorporate all of those into making some sense of at least the first half of this chapter. So the first couple of sections of this chapter deal with something known as electromagnetic radiation. And you may wonder, why do we need to talk about this when we're looking at the electrons? Well, this actually forms a really good basis for understanding the behavior of electrons. So electromagnetic radiation is often abbreviated as EM radiation. And it may seem sort of exotic, but it's actually something that we encounter all the time. Radio waves are examples of electromagnetic radiation. Your microwave oven uses electromagnetic radiation. The colors that you see, visible light, is an example of EM radiation. And then if you have an X-ray taken at the doctor's, for instance, that would be another example of EM radiation. All right, so this is something that we're always exposed to, something that we're always encountering on a regular basis. So all types of this EM radiation, electromagnetic radiation, including light, visible light, all right, they consist of particles, and this is the key thing now, that moves as waves of energy. All right, and that's the key thing that we're going to focus on here. We're going to focus on EM radiation as waves, and then we're going to take a look at some of the characteristics of waves. All right, so when we look at waves, we're going to draw the analogy to just regular waves that you may be familiar with, waves in the ocean, for example, and we're going to make some comparisons to those types of waves and then regular EM waves as well. All right, so when we look at a typical wave, your book has a couple examples, but we'll just do our own example here. If we consider this as our frame of reference, this line, we can have a wave that goes along that line like this. So it starts over here, it goes up, goes down, goes back up, and it goes down again. All right, so you'll notice here that in this particular wave, there are a couple things that we can notice. There's a crest, or the top of the wave, which is this region right here, and then there's a trough, the bottom of the trough, which is down here. And if we were to continue this wave a little bit, all right, we would see that it would continue on further, and it would look like that. So a couple things that we can denote here from our wave that we just drew. The distance from the top of one crest to another, so this distance here in purple, this is called a wavelength. Or lambda is the name for it, and lambda has a symbol that looks like an upside down Y. All right, and that means wavelength. Overall, or generally, we can say the wavelength is the length of the wave, which is the distance from one point to another point further down the wave that's equivalent to it. All right, so we choose the top of the crest because it's easy to find those. We could also say the bottom of the troughs we compare these two, this would be one wavelength as well, or lambda. All right, and these would have the same lengths in this particular wave, because it's a fairly uniform wave throughout. All right, so that's the wavelength. And as you can imagine, different types of electromagnetic radiation can have different wavelengths themselves. And we can make a quick comparison here between the different colors of light that you notice. So red light, for example, if you compare this distance here, this wavelength, to the wavelength of blue light down here on the bottom, all right, we can say that blue light has a shorter wavelength. So blue light has a shorter wavelength than red light. So red light has a longer wavelength, or lambda. And we're going to see some other comparisons as we go further. The other characteristic of a wave, in addition to its wavelength, is something known as its frequency. And the frequency has the symbol, looks a little unusual, looks like a V, but it actually is sort of like a stylized V that looks like this. And we refer to it as nu. All right, and the frequency is, as the name suggests, is how frequent the wave is per unit time. And the unit time that we're looking at here is per every second. So in other words, the frequency tells us how many times a wave is able to pass by a particular point per second. All right, and the unit that we use is called a hertz, which you probably have heard of, not the rental car company, but in terms of radio frequency, for example, hertz, megahertz, kilohertz. That's actually a unit of frequency, which means per second. All right, so for example, we can say, 5 hertz, Hz is the symbol for hertz. This means 5 cycles per second. Okay, because hertz means cycles per second. So the other thing that we can use when we start looking at waves generally, in addition to their wavelength and frequency, is the speed at which all electromagnetic radiation travels. All right, so all EM travels at the speed of light, which has a symbol c, and you can think of this as sort of the speed limit of the universe. And that's very, very fast, right? Light moves at an incredible speed. And light, as we said, is an example of EM radiation. And all EM radiation moves at the speed 3.00 times 10 to the 8 meters per second. So that's 300 million meters per second. All right, think about that for a second. That's extremely, extremely fast. So all of those three things we just mentioned, the wavelength, the frequency, and the speed of light, are all related. So we can say wavelength, frequency nu, and speed of light c are all related according to the wave equation. Okay, and this is where the math is going to come in now. We're going to do a little bit of algebra on this. So the wave equation is written down here, and it says c, the speed of light, is equal to the product of the wavelength times the frequency of that particular form of radiation. All right, so we can say c, the speed of light, is equal to the wavelength of that particular radiation times nu, which is the frequency. All right, and if you wanted to, you can rearrange this equation. Okay, we can solve this. For any variable. Okay, so for example, if we have to solve this for wavelength, all right, then what we can do is we can take our c equals lambda times nu. If you want to isolate lambda on one side, we can divide this right side here by nu, and whatever we do to this side, we have to do to the left side. All right, so the frequency cancels, so we end up with lambda being equal to c over the frequency. All right, so it does involve a little bit of algebra, but we've done this before back in the earlier chapters, right? We're just applying it now to this particular example. All right, so we'll take a look at some examples of those calculations in a second. There are a couple of relationships though that we need to be aware of. All right, and that is the what happens to the wavelength as the frequency changes, or what happens to the frequency as the wavelength changes. And that's because we can develop those relationships because the speed of light, c, that's a constant. That does not change, right? That's what constant means. So if we use our c equals lambda times nu, and we're saying that c doesn't change, well, what would happen if lambda decreases, right? If this thing here goes down, in order for the product of lambda and nu to be the same number, then obviously then the frequency has to go up. And then similarly, if the wavelength increases, well, then the frequency has to decrease. All right, so we call this type of a relationship, we call it an inverse relationship between the frequency and the wavelength. All right, as one goes up, the other one goes down. And as one goes down, the other one goes up. That's what inverse actually means. All right, so as we can summarize that, we can say longer wavelengths have lower frequencies, shorter wavelengths have higher frequencies. All right, and the different types of EM radiation are going to have different wavelengths, frequencies, and also energies associated with them. So when we look at all the different types of electromagnetic radiation, we can talk about them as belonging to part of this huge spectrum of EM radiation. And the light that we see, visible light, actually only makes up a very, very small part of that spectrum. All right, visible light that we're able to detect with our eyes only makes up about 400 to 700 nanometers in terms of wavelength. Right, this very small region right here is where visible light exists, but the spectrum is huge. Right, it's a huge spectrum. On one end of it, we have really, really long wavelengths over here, like radio waves. And on the other side of it, we have really short wavelengths. With things like X-rays and UV or ultraviolet rays and gamma rays, which are things that come from outer space when stars explode. And everything in between, right? You have your microwaves, radiation that's from your microwave oven. You have infrared radiation, which is what heat is. You have your visible light. You have UV rays from the sun, X-rays from your doctor's office, etc. Now, what you'll notice here is that inverse relationship, right? Where you have long wavelengths over on this side, okay? That corresponds to a really low frequency, right? 10 to the 4, 10 to the 5, which is, 10,000, 100,000 per second. On the other end of the spectrum, where you see really short wavelengths, the frequency is much higher, right? 10 to the 19, 10 to the 18 hertz. And that's where that inverse relationship comes in. The other thing that you'll see down here on the bottom is the different energies associated with those different types of EM radiation, right? So things like radio waves, for example, have really low energy. And that's a good thing because we're bombarded with radio waves all the time, and we don't feel the effects of that. But other things like UV rays, ultraviolet rays, and X-rays have huge amounts of energy associated with them, which is why we want to limit our exposure to them. Okay, so the last thing I want to talk about in this section is how we do some of the math using the wave equation. All right, so I'm going to change this question up here a little bit. Let's just scratch that off. So let's say the frequency of a particular light, let's say it's blue light, is 6.3 times 10 to the 14 hertz. And then we're asked, what is the wavelength in nanometers, nm, of this light? All right, so a couple of things to note. When you approach the problems like these, you want to arrange the information, organize the information, just like you've done with every other problem you faced. So what are you given in the first place? Okay, we're given the frequency, which is nu, is 6.3 times 10 to the 14 hertz. Okay, and remember, this means per second, so we can say it's 6.3 times 10 to the 14 cycles per second. This is an S down here. All right, we're also given the, well, we're not given the wavelength. We need to find the wavelength, which is lambda. We don't know what that is. So what relationship do we know exists between frequency and wavelength? What relationship can we use? All right, so here we can use the wave equation, which is c is equal to lambda times nu. All right, and c is the speed of light, so 3.00. You don't have to memorize that. That'll be given to you if you need it. Meters per second. All right, so here our unknown is the lambda that we need to solve for, and we already went through and solved for this. So we're going to solve this for lambda. So we're going to divide both sides by nu. So we end up with now lambda being equal to c divided by nu. And guess what? We know what c is. We know what nu is. We can then substitute those into our equation. All right, so we end up with lambda being equal to c, the speed of light, 3.00 times 10 to the 8 meters per second, divided by our frequency, which was 6.3 times 10 to the 14 hertz, which is per second. All right, so we can see here now that our seconds can cancel out. So the only unit that we're going to be left with is meters. All right, so our lambda, our wavelength here, is going to be equal to, so if we plug that into our calculator, again, what we'll get here is 4.8 times 10 to the negative 7, and then the only unit left is meters in our setup that we have here. All right, but we want not meters, we want our wavelength in nanometers. All right, so this is where incorporating your metric prefixes are going to be helpful. So now we can take our number that we have here in meters. We're going to use our metric relationship now. For every meter, we have 10 to the 9 nanometers. So meters go away. And what we end up with for our wavelength is, now let's see, that'll be 4.8 times 10 to the 2, which is the same as saying 480 nanometers as our wavelength. And this is, we said initially this was blue light. Yep, it was blue light to begin with, right? So this wavelength makes a little bit of sense, right? If you go back to your electromagnetic spectrum, right, you'll see this is where blue light actually resides on that spectrum, right? It's somewhere in this region here, or 480 nanometers. All right, so you're going to have to do several of these types of calculations, especially in your study module. So that's why I wanted to kind of walk you through how to use that wave equation to solve it.